we left off right here. And I mentioned in the last time, these are trig identities right here that are going to be especially important, and I have them summarized here. Yeah, this is the slide. Okay, these are trig identities that you are going to have to be familiar with. I got them all on one slide. This, by the way, was a student suggestion to take them all, put them on one slide somewhere. So just remember at the beginning of chapter 8, like the third slide in, you got your trig identity. You're going to be needing these other times too. But I'm not going to derive them all or anything, but these are the fundamental ones I was talking about earlier. We don't use the cosecant cotangent one so often. Okay. But there is another one we could put here. That is cotangent squared x plus 1 is cosecant squared x. But we don't use that one so much because these will handle the cases we need. All right. This next block right here, this group here, is the same as the last slide. That's these down here. Right. So those are, we've already used these a couple of times. Double angle formulas, I cannot stress how important these are. Sine 2x, 2 sine x, cosine x. And then for cosine 2x, cosine squared minus sine squared. By the way, these all come from these down here. These are the sine and cosine addition formulas. Addition and subtraction. If you put, for example, this top one right here, if we want to look at this guy right here, we'll look at that guy. Where does that come from? Well, down here, if we made this u, and made the u, and made that u, so this is the cosine, this is the sine of 2u, 2 times an angle. Well, you have sine u, cosine u, sine u, cosine u. That's 2 sine cosine. That's where that comes from. Right? Similarly, this formula comes from the cosine formula. Because if you made that u, you made that u, you made that u. One difference here is that for the sine formula, this sign in the middle is always the same sign as that. And I mean SIGN. Those are all the same. These, on the other hand, these two are always the opposite. That's what negative over plus means. That means that's the opposite of whatever's here. All right. Have you ever seen those before? These? They're part of usually a trig class. Did you have, remind me, did you have a trig class somewhere, or how did you? I had it in high school. Oh, okay. But you didn't get to this. Oh, dear. Oh, dear. Okay. Well, these you got to know. They're on the formula card. I know that's a little consolation. But if you had u, this is 2u here. You see here you're going to have cosine u. That's cosine squared right there. And then sine u. Actually, I put the u on the wrong one if that's a u there, right? That is sine squared. Now, erasing all those, we can then use the, once we have this relationship established, we know that, for example, cosine squared is 1 minus sine squared. Cosine squared is 1 minus sine squared. Well, that's 1 minus sine squared minus sine squared. That's 1 minus 2 sine squared. That's where that comes from. And there's sometimes that this is the more convenient one to use right here. I would never use this one here. Why? Because for that one, you need cosine and sine. For either one of these, you just need one or the other, cosine or sine. So here, if sine is 1 minus cosine, let me erase some stuff here. If this sine is 1 minus cosine squared x, well, you have cosine squared minus a minus cosine squared. That's 2 cosine squared. And then minus a 1 is minus 1. So these two bottom ones here, these two bottom ones right here, they derive from plugging 1 minus sine squared or 1 minus cosine squared into this fundamental one here. All right. These are the even and odd identities. This is even. This means odd. Right. The cosine of an angle is the same as the cosine of the negative of that angle. And if you remember the cosine curve, cosine looks like this. And so if you take an angle, say that angle x, it has this cosine right here. That's the cosine right there of that angle. But negative x also has that same cosine. Negative x, it also goes to the same angle because cosine is an even function. And then this one, the odd function, that's because sine behaves differently. Sine looks like this. So if I pick a number x, the sign of that's up there, but negative x has the sign down here. It's got the negative of what the sign was for the positive angle. Okay. We're gonna go through three main types, and then a few oddballs. Okay, and these types are going to have subcases. Personally, I don't so much memorize the subcases, the subcases. I don't. After a while, you can do these problems without memorizing these subcases. Here's the key. Here's the key. You're going to be looking at m and n. So if I want to integrate something that's sine to one power, cosine to another power, I'm going to be looking at m and n. M and n. If either one of them is odd, that's the easiest case imaginable. If either one of those is odd. And the reason why is we can convert sine squareds into cosine squareds by doing sine squared is 1 minus cosine squared. We convert it. We can do cosine squareds into sine squareds. Now, the reason why an odd one makes it easy, so like here in this first example, sine to the fourth, cosine to the fifth. The reason why that makes it better is the derivative of sine is cosine. So we're going to do this. Watch what we do. It's a very straightforward principle, which is why it's a good starting case. This is integral sine fourth x cosine fourth x. And I'm going to peel off one of these cosines. I have a cosine to the fifth. I'm going to write that as cosine to the fourth times cosine to the first, so to speak, right? Dx. So when one of these powers is odd, I can take the odd one and peel off one of those. So I took one of those. It's no longer odd. It's even now. I move it over there. And we're going to save that. And this guy, we're going to convert into sines. Then what will I have? What am I going to have? I'm going to have sines to a bunch of powers here, all times cosine. So if I have sine to these powers, all times cosine, well, that's a function to a power times its derivative. I don't know if that's clear. If I have over here sine x to whatever power, call that, I don't want to use it imminent here, call it k power, times cosine x to the first power. This equals so I have a function there, cosine, sine, I'm sorry. I have sine to a power times its derivative. So this is u, and that's du. So this is like u to the k du. What's the antiderivative of that? So the integral of that, dx, is going to be this to the next higher power, sine to the k plus 1 power, divided by k plus 1 plus c. So we're going to convert this guy here, this cosine to the fourth. We're going to get rid of all the cosines, convert them all into sines, and I'm going to have a bunch of sines to all these powers, all times cosine, which is their derivative. So all of these are going to be sines times a cosine of this form up here. All right, now, what do we do? Go over here. Sine to the fourth. Cosine to the fourth is cosine squared squared. Cosine to the fourth is cosine squared squared. I'm going to plug in for cosine squared. Cosine squared is 1 minus sine squared. So I plugged in for the cosine. Now, believe it or not, we're going to have to multiply all this stuff out. Oh, there's an x missing right here. That red stuff squared is what? So 1 minus sine squared squared is this. Now I'm going to multiply the sine to the fourth all the way through. Let me see here. How much do I want to multiply it? Okay, just once, I'm going to multiply this all the way out. Everything. So all these terms in these parentheses get multiplied by sine to the fourth cosine. So this is going to be integral Sine to the fourth times 1 times cosine is sine to the fourth. Did you see how that one came about? Sine to the fourth over here, cosine there, all times 1. Minus 2, I have a sine squared, sine to the fourth. That's sine to the sixth, x cosine x. Then I have sine to the fourth times sine to the fourth. That's sine to the eighth times cosine x. And I want to show you, make sure you understand the desired result, because when you understand the desired result, that tells you a lot of what needs to be done here. Because all these now, this one is sine to the fourth power times its derivative. So this first one is sine x to the fourth times cosine x. And so I have the derivative of the inside on the outside. So I just add 1 to the exponent divided by the new exponent. And that's the form of all of these, or in that form. Now, I'm not going to use so many steps in the future. I'm going to save you tons of money on ballpoint pens. Because we're going to save some writing. So this is going to be sine to the fifth over 5. Period. That's a sine to a power times its derivative. I have a 2 here, extra 2 on this one. So this is going to be a minus sine to the 7th power divided by 7. So it's going to be minus 2 divided by 7 sine to the 7th. Then sine to the 8th, that goes to sine to the 9th divided by 9. All plus c.
So you just got rid of the cosine?
Yeah, because that's the derivative, right? This right here is sine x to the 9th power, or to the 8th power times cosine. So this is my u, that's du. So you take u to the next higher power, divide by the new power. And just the same way as if I took the derivative, if I went over here and I did d dx of sine x, say to the 9th, what would that be? I'd bring the 9 down. That's going to be 9 sine x to the 8th. Then the derivative of the inside pops out, cosine x. So with the chain rule, the cosine pops out. U substitution is the chain rule backwards. So if you go the opposite direction, that cosine goes back in to make that a 9th power. And that's what happened to the cosine on all these terms. It goes away. That's why we needed the extra cosine. That's why we needed this guy right here. That is why we needed this joker right here at the beginning. That was going to be my extra cosine that wound up on all these terms. That cosine wound up there. It wound up there. It wound up there. Once I distributed. Everything else is signs. So you have sines to a power times the derivative of the sign on the outside. This is the fundamental, and if you don't understand this, Cassie, please stop me and let's talk about it. This is the fundamental relationship that's going to be this whole section. Is we're going to have trig functions to powers times the derivative of that trig function. That's what we're going to be doing this whole section. That's the big confuser. This is the easiest case. The easiest case is when you have either one of these is odd. All you need is one of them to be odd. If this was odd, that would be no problem. If they were both odd, that's no problem. Okay. But one of them has to be odd. Because when you do odd, you can peel off one of them, make that even. So you have sine, say, to the fourth power. You can make that 1 minus cosine squared. You convert it all to cosines in that case. So this is where the trig, all that harping I did, remember last semester I did a trig quiz at the beginning. If I had that to do over again, I'll be honest with you, I would have put all three of you in the trig class. Because I think trig was weak with all three of you on there. And I think grades suffered for that. It was a 1-hour trig class that brought you up to speed. Anyway. By the way, no, it's not true. This one, notice the sign is to the odd power. So you're going to peel off a sign here. And you're going to have cosine 6th, sine to the 4th, and you're going to have an extra sign left over. That sine to the 4th, you're going to convert to cosines with 1 minus cosine squared. That's the sine to the 4th, like we did here for the cosine. Right? That cosine to the 4th was 1 minus sine squared. So this part right here is, I should do that. I'm going to isolate that. That cosine squared, that's squared, it got converted to 1 minus sine squared. That's key. Here, you're going to be doing it with the sine. You're going to peel off one of the sines. Then you're going to have sine to a even power times a bunch of cosines. So you're going to have a bunch of cosines. Now, keep in mind, the derivative of cosine is negative sine. Here, the derivative of the sine was a positive cosine. So you're going to be playing here with some negative signs. And you're going to have negatives in your answer. Sine to the 5th. Sine to the 5th. Well, where's the cosine? Yeah. So we're thinking sines to powers times the derivative of cosine. There's no cosines. But we do have, think of this as this. Think of this as cosine to the 0 power. That's 1. Think of it that way. So you have cosine to an even, sine to an odd. Cosine to an even, sine to an odd. That's the homework. This is cosine to an even, sine to an odd. Basically, this is going to be your homework will parallel what we do here. What did I say to do? Whatever one is to the odd power, maybe both of them are to the odd power. That's even better. But the sine is to an odd power. I'm going to peel off that one of those signs, and I'm going to turn it into, I'm going to leave it. And I'm going to turn the rest of the signs into a cosine. All right? So this is going to be what? And that cosine to the 0, I'm going to ignore that. Because that's 1. So I'm going to do this. Integral sine to to the fourth x times sine x dx. That's sine to the fifth, right? Put in an extra step. This is integral. The sine to the fourth is a sine squared x squared times sine x dx. This is the sine to the fourth. But we have a formula to convert sine squared into cosine squared. So this is going to be integral. That squared is going to be 1 minus cosine squared. So the sine square, all of a sudden I got a bunch of cosines. Those are going to square out, right? We're going to square those, so that's going to be one minus cosine squared squared. Now I have a bunch of stuff times sine. And I'm going to distribute that sine now inside the parentheses. Sine, that's sine x times 1 is sine x. Minus 2 cosine squared x times sine x plus cosine to the fourth x sine x x. These are going to actually integrate a little bit differently, slightly. Now keep in mind, the derivative of cosine is the negative of sine. So that means the integral of cosine is the negative of cosine. Integral of sine is the negative of cosine. The derivative of sine is minus cosine. So that means the integral of sine is also minus cosine. Now, ask yourself, what function has a derivative of plus cosine? Well, what I would like to say here is this. You know what? I'm going to put one more step in before I do that. Integral sine x. Now, here I have cosine to a power. What's the derivative of cosine? Negative sine. So sine is not the derivative of cosine. Negative sine is. So I'm going to make this, I'm going to convert that negative to a plus 2 cosine x squared times now I want you to stare at that until you're convinced that's true. First of all, cosine squared, that's cosine x squared. I need the derivative of the inside on the outside. The derivative of the inside is not sine, it's the negative of sine. So follow me here. This negative sign here, this negative sign here makes that a negative sign. We got too many signs here. This subtraction sign makes that sign a negative sign, and we turn that subtraction to a plus. So do you see how these two are the same? You're not convincing me. If the answer is no, that's okay. I have cosine to a power 2, so I need the derivative of the inside on the outside. I need the derivative of the inside on the outside. Well, the derivative of the inside is a minus sign. So think of it this way. I need to put a minus here. I need to put a minus there to get that to be the derivative. Well, that means I put another minus out here. So that's a minus and a minus becomes a plus. I need to put a minus there to make that the derivative of cosine. But I've got to compensate for that negative sign by putting another negative sign out here, which makes that a plus. Don't worry, we have exactly the same thing on this last one. That's why I put this extra step in, by the way. We're going to be skipping this step in the future. But cosine to the 4th, that's cosine. This is cosine x to the 4th. Don't put a plus there yet. What's the derivative of the inside? Negative cosine, or negative sine, excuse me. Negative times negative sine x. So I had to put a minus sign in there to make that a minus sign. I had to put that to make that negative, to make that derivative of the inside. So I need to put another negative sign out here. So that plus goes to a negative. This will drive you bonkers until you're used to it. It will take some getting used to. But back to what I was saying before. If your derivatives of trigonometric functions aren't ice cold by now, it's not going to go well. It won't go well. So now we're going to have now we're ready to integrate. This is sine. Its antiderivative is negative cosine. And you can always check by taking the derivative of negative cosine. The derivative of positive cosine is negative sine. The derivative of negative cosine has to be the negative of negative sine, or just sine. This one, we have a 2 plus 2 divided by 3 cosine to the 3rd x. Here, cosine to the 4th times negative, that's going to be a cosine to the 5th, right? Excuse me. So it's going to be minus 1/5 cosine to the 5th x. In each case, doing the chain rule in reverse, this minus sign goes inside, goes back inside. Just the same way it pops out with the chain rule. When you do it in reverse, it's back in. And that plus c. It's about time for a crash. So I'm going to save it and get out of here. Let's see if I can avoid a crash. Here. Try it again. Okay, that's what we just did. What was the key here? The key was recognizing you had sine to an odd power. That is where you start. Sine to an odd power, you're going to peel off one of the signs and make it sine to one less power. And now the one less power has to be even, excuse me. This has to be an even. If this were a sine to the fourth, that's a whole different bucket of fun. We're going to get to that one. So if this were sine to the fourth, think of what would happen. If I pulled a sine off like this, I'd wind up with a sine to the third. But a sine to the third, I can't substitute 1 minus cosine, 1 minus cosine squared into sine to the third. I'll have another extra sine left over. So this sine squared, that is converted to that. And I don't like the way I do that. I'm so inattentive at certain things. Okay. Expand that. Now, what this sign out here isn't exactly the derivative of all these cosines yet. You got to have a negative. Now, it's almost easier to leave this sign on the outside and make it a negative and put a negative out here. And that's what we're going to do in the future. I'll show you. So when you're integrating sines, cosines, you got to have a negative sign on the outside for its derivative. Whereas if you're integrating sines to various powers, a positive cosine on the outside is enough. You don't have the negative signs to deal with. Messy case. If they're both even. What have we done up to now? We've peeled off a odd power to make it even, and then you converted everything to sines. Now think for a second. Don't write this down. If I were to convert this right away to 1 minus sine squared x, that's cosine squared, right? What would I get in the next step? I'd be getting integral sine to the fourth times 1, and then sine to the fourth times sine squared. That looks nice. Only problem is we don't know how to integrate that. Well, conveniently. I would like to have sine to the fourth times a cosine, but I don't have the cosine. You see, I don't have that odd power to peel one off. Sine to the sixth, I'd like a cosine, but I don't have it. So all that green goes away. What do you do? Remember what I said those new trig formulas were for this section? Those guys right up there? We have to use them. A lot. A lot. I don't mean to be silly, but I'm not kidding. When it's all even like this, you got to convert them all using this. Now, sine squared is 1 minus cosine squared, right? That's what we were using in the last couple of problems. But sine squared is also this. Okay. By the way, those. Let's go back a second. Our trig page here. Those are right here. Here. Those come from these. Those come from these. In this one right here, what if I solve for sine squared x? Because this is cosine 2x, right? So in this relationship here, if I solve for sine squared, in that relationship, I have this. And if I solve for cosine squared in this relationship, I would have that bottom. So these are all in one big happy family. Right? They're smiling and they're all, that's their safe zone. Right? No masks in that family. They're all one family. You might argue they're all infected. So what do? Massive application. Did I say massive? Massive application of this. Massive application of this guy here. So let's rewrite this. I want to get rid of the green. I'm going to rewrite this as integral sine squared x squared times cosine x. This is going to equal sine squared is that, use that formula up there. You know what I'm going to do? I'm going to erase that. I'm going to write the same thing, but with some red ink. So the sine squared goes to that. Then the cosine squared goes to bothered by one thing here. Bothered by something here. No, okay. All right. Let's deal with some constants. This 1/2 squared is a 1/4. Then I have a half over here. Half times a 4th is an 1/8. I'm going to bring that 1/8 all the way out. So I'm going to go down here, bring 1/8 all the way out there. Now, integral. Oh dear. Bracket. 1 minus cosine 2x squared is 1 minus 2 cosine 2x times plus cosine squared 2x it's that times 1 plus cosine 2x. It's about to get messy. Really, really messy. It's about to be, why did I take this class messy? We got to multiply those. Trinomial by a binomial. 1/8. So what I'm going to do is I'm going to take this trinomial and I'm going to multiply it all by 1. Right? Then I'm going to take the trinomial and multiply it all by cosine 2x. Now, you got to make sure you understand what you're doing, what you're writing here. And you're going to need that second page right there. Big time. I took this binomial, I took the 1, multiplied it by all that in the trinomial. Then I took the cosine 2x and multiplied it by everything in the trinomial. So all of these got an extra cosine 2x on them. Cosine 2x times 1 gave me this term. Cosine 2x times minus 2 cosine 2x gives me minus 2 cosine squared 2x. Then cosine 2x times cosine squared 2x is cosine cubed 2x. I want my money. And a cup of hot chocolate. And a cookie. All right, so let's combine some of these. Cosine minus cosine, minus 2 cosine 2x. And we have a cosine 2x here. Those two can combine. So we're going to combine some. One stays 1. Minus 2 cosine 2x plus cosine 2x is minus cosine 2x. So we're going to combine like terms. Then I have a cosine squared 2x here, minus 2 cosine squared 2x there. So that is a minus cosine squared 2x. And then I have the cosine cubed on the end. You're not going to believe this. We have 4 terms. 4 terms. They all integrate differently. With different all these are in different forms. All these are in different forms. 1 integrates just to x. That was easy. Right? Minus cosine, I'm going to try to get all these ready to integrate, but I'm not going to be able to in one more line. I'm not going to be able to. So 1 is already ready to integrate. This is actually ready to integrate. Right? That would integrate to sine 2x, minus sine 2x, and then a constant on the outside. So this one is actually relatively ready. This one has a squared in it. How do we integrate cosine squared? Not with 1 minus sine squared. We integrate this cosine squared by using that. It's true. Okay. And then cosine cubed. Cosine cubed. Well, that's cosine to an odd power. I'm going to pull off a cosine and I have a cosine squared. And I will convert the cosine squared into 1 minus sine squared. Let's do one line. Hopefully this will explain it, okay? 1/8. This one, integral. 1 is okay. It's ready to go just the way it is. Cosine 2x is actually ready to go, except I'm going to do one little thing here. I'm going to go, let's see here, minus 1/2 times 2 cosine 2x. You see, I put this 1/2 and 2 in there. because I'm going to need the derivative of the 2x on the outside. This next one, minus, careful, gasap. Gasap. 1/2, 1 plus, notice here in our formula, this is double that angle. Now, the one I'm doing, I already have a cosine 2x there. So this is going to be a cosine 4x. Yeah. So this is going to be a cosine 4x. And this bugs me here. I'm going to put that in red too, just so people can see what we're doing. So that one's ready to go. Well, kind of. We're going to do some combining. What about this guy? Okay. This is actually a function of a function of a function. So we would need double U substitution here, which I'm not going to do. I'm going to do it a different way. Watch this. I'm going to peel off a cosine 2x. So I'm going to write this last one as, this one, as cosine squared 2x times cosine 2x. So I've cosine to an odd power there. This guy, I'm going to convert to 1 minus sine squared 2x. And then I'm going to have cosine 2x out there, which is just derivative. So this is going to be, okay, 1/8 integral bracket 1 minus 1/2 2 cosine 2x. That's ready to go. Now I have to distribute this 1/2. I'm going to get a minus 1/2 minus 1/2 cosine 4x. What do you know what I'm going to do? I added this 4 times 1/4 here because I'm going to need that 1/4 right there. Actually, I did that in reverse. I need to do it this way. And this one is going to get a we've done a lot of writing. We got a lot more to do. So I'm going to actually save this. Get out of it. So I don't want to lose that page. Should have got the slide number before I did that. Okay. Okay. We're going to multiply. Oh, this is going to be very interesting. Okay, very interesting. This right here, I'm going to do something I haven't done yet. But 1 times cosine 2x is a cosine 2x. Then minus sine 2x squared times cosine 2x. That is this part right here. Oh, you know what? I just saw something. This is amazing. Right? That's a plus cosine 2x. There's a minus cosine 2x. Those cancel all together. Because this right here was a minus cosine 2x. Remember up here? Before I put that in there? Because I put that in there anticipating integrating it, but it turns out I don't need it. Okay. So I'm going to write one more clean line here. And I'm going to combine like terms. Believe it or not, we're almost ready to go. 1/8. We have a 1 right here. You see that 1? Then a minus a half right here. So 1 minus a half is 1/2. This guy right here is minus 1/8 cosine 4x. That's ready to integrate. Oh, 4. Cosine 4x. And then on this last mess here, I have this part here. I got one thing I need there, though. Now watch this carefully. I have sine 2x squared. I need the derivative of sine 2x on the outside. The derivative of sine 2x on the outside. Pop quiz. What is the derivative of sine 2x? The derivative of sine 2x.
That face that is usually covered by our thumb. That face with
The derivative of sine 2x. Because I need the derivative of the inside on the outside. How'd you do? The derivative of sine 2x is going to be cosine 2x, but I need the derivative of the 2x to come out. So I need an extra 2 here. And that means I need a half here. Yeah. I've been too easy today. No pop quizzes on that, right? We are, I think, ready to integrate. Isn't that exciting? It's so exciting. Hey, Jesus, you're watching this, right? One eighth bracket. Antiderivative of 1/2. 1/2 x.
that was easy.
Antiderivative of this, 4 cosine 4x, that integrates up to sine 4x. And then I have a minus 1/8 in front of it. And in each case, think of a derivative. What's the derivative of sine 4x? That's going to be cosine 4x times 4. That's what we needed that 4 for, because the derivative of that 4x would come out as a 4. Next one. Minus 1/2 sine 2x cubed over 3. And all of that is the derivative of the inside. So if this is u, if that's u, all of this is du. So that's going to be sine cubed over 3. So now I have a 1/3 times sine 2x cubed. Almost done. And one more line. This right here is 1/6, right? Minus 1/6. I got to distribute that 1/8 inside. So this is going to be 1/16 x minus 1/8 of 1/8, 1/64 sine 4x. Then 8 times, this is 1/6, 8 times 1/6, or 8 times minus 1/6 is minus 1 over 48. And this is sine cubed 2x plus c. Now, I would normally ask you if there's any questions. But I don't trust you. I think you have. So I'm going to go through it again. Okay, I'm going to go through it again, and just to review the key spots. What are the hot spots here? Well, hot spot number 1 is recognizing these, using these. So this is hot right here would be hot spot number 1. You got to use these formulas up here. And you're recognizing these are both even. If one of them was odd, we would peel off that off of the odd one to make 2 trig functions, sines and cosines, to even powers times the one we peeled off. But we can't do that. So we have to convert them all using this. Yeah. And so when we plug this stuff in, we wind up with, like I told you, a mess. Right? Because you have to square this, square all that. It's there. The 1/2 gets squared. That makes a quarter. A quarter times the half over here puts an 1/8 on the outside. My recommendation is get rid of any fraction you can get on the outside, do it. But that leaves us with a trinomial times a binomial. So this has 3 terms, that has 2 terms. Your product is going to have 6 terms. And the way I do this is I go to the binomial. I took 1 times everything, and that gave me that much. 1 times all that gives me that. Then I took cosine 2x times all that, and that gave me that. That left me with some like terms. Add some like terms. Combine like terms. Always combine like terms. This guy, this guy, and this guy combine. And then this guy and this guy combine. And so we wind up with 4 terms instead of 6. Now what to do? 1 is already set up to integrate. Just goes down here. Cosine 2x, I need a 2 on the outside, so I do 2 times 1/2. It turns out that canceled anyway. That's why I did it. That canceled with that other one. Cosine squared 2x, I don't know how to integrate without doing that half angle formula again. All right, and that gave me the 4x here. Yeah, another 1/2 right there. And then this is cosine to an odd power. I peeled off one of the cosines, which I'm going to turn into the derivative of the inside once I convert it. So I would say this is a hot spot right here. Oops. This is a spot I would pay careful attention to, right? And this cosine squared 2x goes down to 1 minus sine squared 2x. And all that gets multiplied by cosine 2x. That gave me a cosine 2x times 1, that cosine 2x, which perfectly cancels with this cosine 2x. Gets out of our life. Yeah. Then the next big problem that it's not a huge problem if you understand U substitution, if you understand the chain rule. If you understand how derivatives go, you'll understand why, first of all, you need the cosine 2x out here, and you need the 2 out there, because this 2 is the derivative of that 2x. That would pop out. Put differently, sine 2x cubed is 2x plugged into sine x, plugged into x cubed. So it's a function of a function of a function. That means you're going to have a more complicated derivative. You have the chain rule there twice. You have U substitution twice. And so I would say this is a huge, huge sticking point here for people who are rough on derivatives. Okay. But I warned you all this was coming. It doesn't stop in chapter 8. It just keeps going. So I do a little cleaning up here, right? The 4, I got the 1/8 there. This now goes to, it's time to integrate. I've now made that a perfect 2x. I have a u on the inside. I have du on the outside. So that goes to sine 2x cubed over 3. And there's the 1/3 sine 2x cubed. Okay. Then I distribute the 1/8 in from the outside, and we get a final answer. I'm going to move some of that down there. There you go. This is a much, much more polite version of what we just did. It's friendlier, right? Because what we just did, we had sine to the 4th cosine squared. Those are both even. Your homework here is sine squared cosine squared. But we've made things a little more fun by making a definite integral. So you will get the antiderivative of that, which I have for you here. Then you plug in the bounds of integration. And that gives you this for your final answer, which is an oddball looking answer. This is just a fun fact. These are a couple of trigonometric identities that have no antiderivatives that are called closed form. You need power series to integrate these. So there's some things you cannot find the antiderivative of, and they've proven this. Tangent x over x, there's no function that when you take the derivative of it, gives you that. They've proven that. And this is a cute little formula. Well, you know what? I think we're going to skip this altogether. We're going to, John Wallace, he proved he was working on things that were kind of pre-calculus before Newton and Leibniz, which were the two Newton and Leibniz, Gottfried Leibniz and Isaac Newton, they came up with calculus independently of one another. Newton came up with it first. Leibniz came up with it second, but he was the first to publish it. So a lot of times it's whoever publishes, whoever gets it out there and makes it known, gets their name on it. Honestly, Newton and Leibniz remained competitors and sometimes not so polite competitors the rest of their lives. Newton was the better mathematician, honestly. But Leibniz, his notation was a lot easier to understand than Newton's was. And so a lot of our notation we got from Leibniz. He came up with this formula here. 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7. All multiplied together indefinitely is pi over 2. Right? And that leads to two integration formulas right here that we are going to skip. Skip that one. And let's see. Skip this one. Those look the same. They're not. And we're going to skip. No, we're going to skip. Yeah, we'll call it good right there. We got that one homework for next time. Sine squared. We had two homeworks for next time, actually. So, yeah, we'll call that good right here.